Okay, our next speaker is Brandon Rayhaun, who's a U Chicago, was a U Chicago undergraduate, and both worked with Jeff as an undergraduate and for his master's, and currently is Stanford, his PhD.
Great. Yeah, so thanks so much to the organizers for giving me this wonderful opportunity to help celebrate all things Jeff. It's a huge honor for me to be here, and I'm especially looking forward to learning more Jeff-related science and stories from you. I'm also glad that we all seem to have made it to the correct Jeff Fest. There was another one being advertised in July, more widely than this one.
That one looks like more fun, though.
I'm not sure if you have to be named Jeff to get into this Jeff. I met Jeff when I was an undergraduate here at U Chicago 6 or 7 years ago now, and I have been very fortunate to have kept in contact with him since graduating. And so in particular, in this talk, I want to give a sort of a very incomplete survey of some explorations that we've been doing in mathematical physics over the years. And everything that I'll say is based on these papers above, which were written with these excellent collaborators pictured here. And I don't know if Ruth is still here, but Jeff also told me that the 3 middle papers there at the end of undergrad would be published by the end of the year. They were 1 paper at the time, and they just came out a few months ago. So, great. So the rough outline of my talk is that it'll proceed in 2 acts. So in the first act, I'm going to talk about a subject called monstrous moonshine and its various offshoots. Most of that work was done in the previous century, but Jeff and I and our collaborators revisited some aspects of it in this century because I wasn't a particularly advanced 7-year-old, so I couldn't have contributed in the previous one. And then in the second act, I'll talk about a sort of second wave of activity in moonshine, which is called Umbral and Penumbral moonshine. And that'll be more modern, and it's currently being actively investigated today as well. So, but before I get into any details, I just want to establish some baseline philosophy that will underlie most of this talk. And that is that the promise of moonshine, and in a sense, mathematical physics more generally, is that in trying to explain connections between, in the case of moonshine, algebra and number theory, one will often be led to discover new unifying mathematical and, in the best cases, physical structures, which not only enrich our understanding of those connections, but also stand on their own as interesting objects to research. So I'll be implicitly taking that perspective throughout this talk, and so my goal will be to explain to you both how this promise of moonshine has already been fulfilled and indications that it will continue to be fulfilled moving forward. So with all those disclaimers being said, let me start with the first part of my talk, which is on monstrous moonshine. And so I'll start by taking the perspective of a finite group theorist. After 100 years of really hard work, actually more, I flashed this Wikipedia excerpt to show you that I'm not exaggerating when I say the classification of finite simple groups took an enormously long time. But anyways, after a bunch of work by mathematicians, those of us living in the year 2022 get to enjoy a nice clean statement of the classification of finite simple groups. Its structure is very similar to the structure of the classification of finite complex simple Lie algebras, in that there are sort of some number of infinite families, like the A, B, C, D families, and in the case of Lie algebras, and there are also some finite number of exceptional cases, which are displayed down here for finite groups. In the case of Lie algebras, the largest of the exceptional cases is this this Lie algebra E8, which has obviously played a very starring role in Jeff's work, and the analog of E8 in the case of finite groups, in the sense of being the largest of the exceptional groups is a group called the monster. And many of the other sporadic groups, I think 20 of them, actually embed in some complicated way into the monster. And more generally, they participate in a very interconnected, chaotic web of relations with one another. And so a finite group theorist with Jeff's healthy appreciation of exceptional objects might have some questions about these sporadic groups. So group theory is supposed to describe symmetries. So the first question you should ask is, what are the natural objects on which these exceptional finite groups act on by symmetries? Another question you might ask is, can we get any additional insight into this weird, complicated embedding diagram of the sporadic groups? Does it appear anywhere else in nature or somewhere? Lastly, do these sporadic groups describe anything close to physics? Okay, so just to give you a preview of where we're going in part one, which I hope will not be too technical, let me give you the statement of the result that we're going to work towards. So we're going to construct a chiral algebra for each node in this graph. Each node in this graph is labeled by an exceptional finite group. And the chiral algebra that we attach to a given node will have the property that it has that finite group as its collection of symmetries. And moreover, this assignment will have a sort of nice property, a further nice property, that if two groups embed into one another, then their corresponding chiral algebras, or 2D CFTs, will as well. Sorry, I should clarify a point of terminology. I'm going to use essentially the words chiral algebra, RCFT, and BOA interchangeably. You might like one over the other depending on what kind of person you are, but I usually use this word chiral algebra, so that's just a disclaimer. And the upshot is going to be that sort of everything to the right of where the pointer is a sporadic group on the nose, actually this one as well. And so by achieving this construction, we will have realized part of the diagram of sporadic group embeddings in a physical context. It's sort of mirrored in the world of 2D RCFT. So the starting point of this construction is going to be something called the Moonshine module. So this is a 2D conformal field theory. All of its correlation functions are meromorphic, and it has central charge 24, and it has the amazing property that its symmetry group is precisely this monster group, which I said earlier is the largest of the exceptional finite groups. The way that one usually talks about this theory nowadays is that you can obtain it by taking a theory of chiral bosons that are based on the Leech lattice. The Leech lattice is another exceptional object. It's the lattice that solves the sphere packing problem in 24 dimensions. So if you take the theory of chiral bosons based on the Leech lattice and you gauge a Z2 global symmetry subgroup of its automorphism group, then you're naturally led to this monster CFT. And I'll just comment that this is one of the first examples of what we would now call an orbifold conformal field theory. And around the same time, maybe slightly later, Jeff and collaborators, Lance, Edwin, and Kamran Bafa, introduced orbifolds as a general construction in 2D CFT. And it goes without saying that they're now a ubiquitous tool in the toolkit of anybody who's ever thought about 2D CFTs. So as I said, the starting point of this construction is going to be the monster CFT. And we're going to essentially take it as a seed theory and manipulate it in various ways until we get new objects that realize some of the other exceptional finite symmetry groups that appeared in previous slides. So what are the sort of general methods for taking a given CFT and producing new ones? Well, one method is to take orbifolds of it, by which I mean gauge discrete subgroups of its symmetry group, And this is a particularly natural option in the context of the monster CFT because it just has so many symmetries available to gauge. In particular, it has like something like 10 to the 53 symmetries, so very large group. And the second method is the method of taking cosets, which will be familiar to people who have thought about current algebras, but I'll review that second construction a little later. So orbifolds by cyclic subgroups of the monster are known in the math literature as, well, the field of study is called Generalized Moonshine. And part of that is a sort of historical quirk, which is that actually mathematicians sort of did calculations related to these orbifolds before really even knowing what they were doing. So specifically, there was a mathematician, Simon Norton, who conjectured that one can assign special modular functions to commuting elements G and H in the monster group. And these functions are special. I'll describe how in a second. But moreover, they're sort of the graded characters, in the sense of group theory, of some big Hilbert space, each Hilbert space labeled by elements G in the monster, which enjoy an action of the centralizer of G in the monster. So the way that these functions are special is that if you take the upper half plane and you quotient it by the subgroup of SL2R, which leaves these functions invariant, then it's always isomorphic to the Riemann sphere, maybe with finitely many points deleted. And so this is referred to as the genus zero property of generalized moonshine. To explain why this is bizarre, we'll use a result of Jeff and Lance and Paul. So Jeff and collaborators sort of embedded Simon Norton's conjecture into a physical context. And what they said is that these functions, TGH, are precisely the functions that you would get if you were computing an orbifold by the cyclic group generated by G. And this VG Hilbert space is precisely what is known in the orbifold literature as a twisted sector.
Or a generalized notion of a physical context.
Yes, I'm using the word physical extremely liberally here. Yes, algebraic, I should say, maybe would upset people less. Alternatively, somebody born after the year 1993 might say that what they were doing was they were wrapping invertible topological line defects around different cycles of the torus, but as you prefer. So these twisted sectors or defect Hilbert spaces are one way to involve some of the other exceptional groups in physics because these centralizers are often closely related to other exceptional sporadic groups. But they're not full-blown modular invariant CFTs, so one might try to do a little better than this. And so that's why we're going to turn to the second method, which is the coset method. So I fear that this is going to get too technical, but I'll try and sort of summarize what taking cosets is in the briefest possible words. So say somebody hands you a chiral algebra V, as well as a subalgebra W of that chiral algebra. The coset is sort of like a generalization of the idea of a centralizer in group theory. So the coset of W and V is defined to be the space of all operators in V which have a regular OPE with the operators in W. And this W twiddle, this coset, is itself a subalgebra of V with central charge equal to the difference of the central charge of V and W. And the tensor product of W with its coset sits inside of V as well as a subalgebra with the same central charge as V. Okay, that was a lightning fast review of what cosets are. And okay, so why do people consider cosets? Well, one reason is it's a very efficient way to obtain new theories from known ones. And I think it's still lore in the field that any RCFT can be obtained as a coset of current algebras, no less.
There's now some evidence against that, actually.
There's now some evidence against that, okay. So Great, so here's an example. Consider the Lie algebra embedding of SU2 into two copies of itself, just embedded along the diagonal. Whenever you have an embedding of Lie algebras, it induces an embedding of current algebras. Current algebras are just sort of the natural structure in 2D CFT you get whenever you have a continuous global symmetry. And if you consider the coset of these two copies of SU2 at level 1 by SU2 at level 2, then you find essentially just by computing the central charge and noting that it's equal to 1/2, that this coset must be equal to the Virasoro algebra at C equals 1/2. So it's essentially the Ising model. And in fact, all the minimal models admit a sort of similar description in terms of current algebra cosets. Okay, great. So we want to apply this coset construction in the context of the monster CFT, but we run into a practical as well as maybe a conceptual problem, which is that the monster CFT just has like a dizzying number of subalgebras that we could contemplate feeding into the coset construction. And we couldn't possibly hope to study them all, so we need some kind of principle that will privilege some cosets over others. And since our interest here is in exceptional symmetry, the principle we're going to use is we're going to demand that these cosets sort of preserve as much symmetry as they possibly can, in a sense that I'm going to now make precise. So for this, let me start by noting that whenever you have what's called a commutant pair, so you can just imagine W is some algebra and W twiddle is its coset. Whenever you have a commuting pair of subalgebras inside of a chiral algebra V, then on general grounds you can decompose V into a tensor product of representations of W and W twiddle. This is very much like the fact that in a sort of more ordinary 2D CFT you can decompose the Hilbert space into representations of its left-moving and right-moving chiral algebra. Except here, everything is purely left-moving. I've just chosen two commuting subalgebras of V. Now, symmetries of V are just maps from V to itself, obviously, but we want to think about which symmetries will sort of descend to symmetries of W and which symmetries will descend to symmetries of W twiddle. And so I claim that if you have a symmetry which factorizes so that in this tensor product decomposition, it's only acting non-trivially on the W's and acting as identity on the W twiddles, then those are precisely symmetries that are inherited by W via its embedding into V, and you can make a similar definition for W twiddle. So I'll call those two subgroups of the symmetry group of V that are obtained in this way G and G twiddle. Now, let me just note that elements of G sort of manifestly commute with elements of G twiddle, and that's simply because they're acting on different tensor factors. And so if you try and commute them, they'll just move right past each other. Another way of saying that is that G lives inside of the centralizer of G twiddle, and G twiddle lives inside of the centralizer of G. And so if you like, this is sort of an upper bound on how big G can get, or how big G twiddle can get. And so what we mean when we say that we want W and W twiddle to inherit as much symmetry as possible is we mean that we want this bound to be saturated. So in other words, if G is equal to the centralizer of G twiddle, and G twiddle is equal to the centralizer of G, then we say that they've inherited as much symmetry as they possibly can, subject to this condition, and this is a coset that we want to think about. So this corresponds to the case that G and G twiddle, this is just terminology, when this condition is true, it's called a dual pair. And consideration of dual pairs is sort of has a long and storied history in the math literature. They're very important for various representation theory things. So this is some indication that we're on the right track. Okay, I eventually want to look for cosets that preserve a lot of symmetry in the monster theory, but I feel like I should start with a simpler setting in which things are a little bit more obvious. So everything I say here is going to sound almost tautological, but it'll be less trivial in the monster theory. So take your V to be the E8 current algebra at level 1. It contains a subalgebra, SU2 at level 1, and its coset is well known to be E7 at level 1. I don't know, does this arise in some important phenomenological application or something like this? I could have sworn I saw something like that in Pierre's talk, but anyways, I'm not pretending at all to do any real physics here. What's happened here is that W, just by virtue of being an SU2 current algebra, has inherited an SU2 global symmetry from E8, and likewise W twiddle has inherited an E7 global symmetry from E8. And it's just a fact about Lie algebras that this pair, SU2 and E7, is a dual pair of commuting Lie algebras. In other words, SU2 is precisely equal to the centralizer of E7, and E7 is equal to the centralizer of SU2. And so this commuting pair of subalgebras satisfies this condition we want, that they should inherit as much symmetry as possible. And so the way I want to think about this is that this statement that there's this commuting set of chiral subalgebras sitting inside of E8 current algebra is a kind of uplift to the CFT world of the purely Lie algebraic statement that E8 has this kind of commuting pair of Lie subalgebras. And we're going to look for similar CFT uplifts of dual pairs inside of the monster. So let me just do one last example. So there are other dual pairs inside of the E8 Lie algebra that you could lift to CFT in this way. But let's just pretend we're a sort of strange person who doesn't know how to construct SU3 at level 1 and doesn't know how to construct E6 at level 1. How would they stumble upon, how could they construct this just from knowledge of the fact that this dual pair of Lie algebras exists without knowing how to construct their corresponding CFT uplifts? So what they could do is they could just notice that at the level of Lie algebras, you can think of SU3 as being generated by two different SU2s sitting inside of E8. And then you could lift each of these SU2s separately to SU2 current algebras inside of E8, and then consider the chiral algebra that they generate together. And the claim is that that will give you SU3 at level 1. Then you can take the coset of that subalgebra, and you'll get 6 at level 1. Okay, so this was a lot, but now having done that, we'll be able to essentially use the same words, but applied in the monster setting, and it'll go a lot more smoothly. So just to restate what the goal is, we want to look for commuting pairs of subalgebras inside of the monster CFT, such that the symmetries they inherit precisely correspond to a dual pair of subgroups inside of M. That is, we want G to be the centralizer of G twiddle, and we want G twiddle to be the centralizer of G. That's the maximum amount they can inherit. In the context of E8, we sort of started by taking a coset of the simplest possible simple Lie algebra, namely SU2. And so in the choice of finite group theory, we have to make a similar choice. And the simplest choice is, I don't know, Z2. Z2 is known itself to participate in a dual pair inside of the monster theory. And its dual is another exceptional sporadic group called the baby monster group. So if we manage to give a CFT uplift of this dual pair, then we will accomplish our goal of obtaining a chiral algebra with exceptional symmetry, namely baby monster symmetry. But what should play the role of W? In other words, what's the theory W that inherits the Z2 symmetry from the monster theory? And it's sort of the most obvious thing you can imagine. It's basically the Ising model. And so there's work of mathematicians which make this precise, and they show that there's a one-to-one correspondence between two things. One thing is order 2 elements in the monster group which belong to a particular conjugacy class called the 2A conjugacy class. and subalgebras that are isomorphic to the Ising model inside of the monster CFT. And the idea behind this correspondence is that this Ising subalgebra precisely inherits its corresponding G from the monster group. Remember, the Ising model just has a Z2 symmetry that we all know and love. And mathematicians have calculated this coset of the monster theory by one of its Ising subalgebras, and they indeed showed that this inherits a baby monster symmetry. So we want to generate a few more examples. And the way that we'll do this is that we'll copy the idea for SU3. We said that SU3 can be thought of as being generated by two different SU2s sitting inside of E8. So similarly, let's consider groups that are generated by a pair of 2A involutions inside of the monster group, G and G prime. The conjugacy class of the product of G and G prime completely fixes essentially the subgroup G that you get, which is always a dihedral group. And bizarrely, the inequivalent choices of this group G that you can get by picking two 2A elements are in one-to-one correspondence with the nodes of the E8 Dinkin diagram. So, for example, this 1A entry here corresponds to the choice of G being equal to G prime. Then the product is just the identity element, and the conjugacy class of the identity element is called 1A, so that's labeled there. And what this says is that the maximum order of G times G prime is order 6, and that corresponds to this node here. So each group G participates in a dual pair inside of the monster, and it's often the case, as we saw with the baby monster, that this group G twiddle is very closely related to an exceptional finite group. And so we just repeat the idea that we implemented in the context of SU3. We take W to be the Ising model, to be the chiral algebra generated by the Ising model associated to G and the Ising model associated to G prime. And then we take W twiddle to be its coset. And the claim of our work is that this pair precisely inherits these dual pairs as symmetries. And so let me just give you a table of theories that you get in this way. So using this construction, you get 5 theories which have sporadic symmetry groups on the nose. These are the ones that are circled in red. 2 of the cases you get are almost sporadic groups, but they're not quite. They're extensions of sporadic groups, which we don't like as much. And then finally, 2 other ones are sort of exceptional groups of Lie type. Groups that you get by essentially taking Lie groups and working over finite fields instead of the complex numbers. So the dream usually is that by playing around with examples, you'll be led to discover new and general structures. So one natural question is, can all the dual pairs inside of the monster group be lifted to commuting pairs of chiral algebras inside of the monster CFT? And more generally, you can contemplate, in the spirit of Galois theory, are there general correspondences between subalgebras of a chiral algebra and subgroups of its automorphism group, which we seem to be finding, at least in this particular example. If it's not the case generally, is this another special property of the monster CFT, or what's going on? And so these are just some questions that I think would be interesting to think about moving forward. Okay, so this was the conclusion of wave 1. How am I doing on time? Did we start at 3:40?
A few minutes after. Roughly 15 or so minutes.
Okay, when do I end?
Well, originally it was 4:30, but we go to 4:35.
Okay.
Yes, can I just ask, you just talked about Z2, you can imagine lots of other ZNs and so on.
Yes.
Have those been considered too?
So Yes, there Z3 and Z4 have been considered, and instead of the Ising model, you use parafermion theory. There's other cyclic subgroups that participate in dual pairs inside of the monster, but I personally don't know. Like there's a Z6, for example, but it doesn't correspond to a parafermion theory to my knowledge. So something changes for these other cyclic subgroups weirdly.
But can you get other sporadic groups that you can't get with the Z2?
Yes, so Z3 corresponds to another sporadic group called the Fisher 24 group. I can't remember if there were.
You had it on that picture.
Yeah. What else is there? Yeah, I think that's the only other one. I mean, these are other groups that you can get by considering like Z4s and stuff. And they're this thing that I didn't like as much, namely extensions of sporadic groups.
Thanks.
Okay, so now I'm gonna move on to discussing some more modern moonshine phenomenology, which Jeff has been very heavily involved in. So what I'm referring to as wave 2 of moonshine, I think started in roughly 2010 with observations that were made in the context of string theory on K3 surfaces. And specifically, Iguchi, Uguri, and Tachikawa studied this supersymmetric partition function known as the elliptic genus of K3. If those words don't mean anything to you, you can just think about it as a same as an ordinary partition function, except it's counting with the sign supersymmetric states in these sigma models with K3 target. Mathematically, it's a modest generalization of a modular form known as a Jacobi form, which you can think of as a modular form with an extra variable, which is sort of like a fugacity that's keeping track of some other charge. And what they did was, K3 sigma models have an n equals 4 superconformal algebra. And so on general grounds, whenever you have some kind of symmetry algebra, you should be able to decompose, say, a partition function into characters of that algebra. And in doing so, you get a bunch of coefficients, an. And they just looked at these coefficients and they noticed they're very closely related to dimensions of irreducible representations of another sporadic group called M24. In fact, the first 5 of these are dimensions of irreducible representations of M24 on the nose. So at the level that I've presented it thus far, this bullet point up, this could just be pure numerology and mean nothing. But actually subsequent work showed that there actually exists a Hilbert space which admits an M24 action, and such that the various partition functions are all Jacobi forms. And so the appearance of the Mathieu group should not be an accident.
Where does this Hilbert space live?
It's just I use Hilbert space to sound less intimidating, but it's just an abstract M24 module. It's a list of the, in each component I just specify what the irreducible representations are. It's not an actual construction of it.
Is that what we call representations?
Sorry, yes.
Oh, okay.
Yes, yeah. Sorry. Did I use the word module?
It's a module.
Yeah. So one's first thought is that history is repeating itself and that the explanation of this is basically the same as it was for the monster CFT. Namely, there should be some point in the moduli space of K3 sigma models which has an M24 symmetry group. And then the fact that you see dimensions of representations of M24 in the elliptic genus is just the statement that the elliptic genus is witnessing the symmetry group through its coefficients. However, there's a no-go theorem, which essentially enumerates all the symmetry groups of every single K3 sigma model at every point in moduli space. And this enumeration shows that M24 does not embed into any of them. So M24 is not a symmetry subgroup of any K3 sigma model. And so the explanation for why its representation theory appears to be related to the elliptic genus of K3 will have to preceded by some more subtle construction. And that's still, I think, fair to say, an open problem, though some progress has been made on this. And
Do we know if the symmetry groups that do appear are in any sense subgroups of M24? Of this
they're
particular-
generally, so it depends on what you're talking about. So if you talk about just symmetries of K3 as a surface, I think the statement is that they all embed into M23, which does embed into M24. But that's not the right concept for sigma models. So if you look at genuine quantum symmetries, then they're generally like no, one group doesn't embed into the other. They're incompatible with each other.
They're all subgroups of the Conway group, actually, Conway 1.
Right. I think there's been
I
some.
hear that, they're all subgroups of one.
They're all subgroups of another sporadic group called Conway 1.
A much bigger one.
How much bigger?
It's a much bigger one.
It's a much bigger group, yeah.
I think there has been an attempt to compare twined parts. Well, maybe let me not try and explain work that I am not that familiar with. But yeah, generally the groups don't really match up in the way that you would expect. Good. So the Mathieu Moonshine problem can be summarized as follows. So at least the BPS sector of this theory appears to be organized by a symmetry structure which is not an actual symmetry of the theory in any of the usual senses. So this, I think, offers a nice opportunity for maybe people thinking about generalized notions of symmetry to get involved and tell us what's going on. Now, you can generalize this Mathieu Moonshine phenomenon, and the generalization proceeds as follows. So the first step is to recognize that you can take those coefficients, an, and repackage them into sort of an auxiliary generating function. This function I'm calling H2. And I'll just comment that it may seem trivial since it only has one independent component, but I'm thinking of it as a 4-component vector valued object, which it'll become clear why in a moment. So it turns out that this is an example of something called a vector valued mock modular form. And I'm not going to describe in any technical detail what that object is, but the basic idea is that whenever you have something you're calling a mock modular form, there's some kind of tension between holomorphicity and modular covariance. So for example, this object is meromorphic, but it doesn't transform covariantly in any nice way with respect to the action of the modular group. However, it can be completed into an object which does transform nicely with respect to the modular group, but the price you pay is that the thing you had to add to it to complete it is non-holomorphic. But anyways, you can study this completion, and indeed you find that it transforms like a vector valued modular form. And in general, when you have a vector valued modular form, you have to tell me what is the representation of SL2Z that it transforms with respect to. So I'm going to call that rho 2 star. And the point is that this representation, rho 2 star, is just a special case of a family of representations that are indexed by a positive integer m, called the index, and which has a dimension 2m. And so a natural question is, we observed that Mathieu Moonshine is related to mock modular forms at index 2. Are there other Moonshine phenomena at different values of n, different values of the index? And Jeff and Miranda Ching and John Duncan answered this question with a resounding yes. And so specifically, they showed that the Moonshine cases are in one-to-one correspondence with Niemeyer lattices. Niemeyer lattices are the 23 even unimodular lattices of dimension 4, if you leave out the Leach lattice. And their assignment was very explicit. So they said, to each Niemeyer lattice, you can associate a group that group is just the automorphism group of the lattice modulo its Weil group, which is the group of reflections through its roots. So actually, it's pretty unfortunate that atrium is blocking M24. It's fine. There's an M24 right underneath the A. So yeah, I'll just keep going. Brilliant. So yeah, if you look at this table, Mathieu Moonshine corresponds to the Niemeyer lattice with root system A1 to the 24, and you see precisely this M24 group here appearing. And they also assign collections of mock modular forms, and the index M of these mock modular forms is equal to the Coxeter number of that lattice. If you don't know what that is, it's basically just well, I will try to explain maybe some invariant that you can associate to the lattice. And finally, they construct abstractly a representation of this group GX, whose graded characters are all the functions from below point 2. Okay.
Can I just say one thing?
Please, yes.
So what you said is completely right, but I just want to say that Atish and Samir and Don Zagye gave us a huge boost towards this by constructing many of these mock modular forms first in the context of black hole counting.
Great. Yeah, it's a nice bit of history. Okay, and one of the last things I want to say is that Umbral Moonshine itself is only half the story. So I'm proceeding in sort of the most pedestrian way, but it'll get you to where we want to go. We generalized from row 2 star to row m star. This was the representation with respect to which the functions we were interested in transform. And to a mathematician, it's unnatural to just consider vector valued modular forms transforming under this representation. They'll tell you to also consider vector valued modular forms transforming under its complex conjugate. And the reason is that various theorems which relate automorphic forms of different kinds only become complete once you include functions which transform like this. And just as an aside, they're also common in physics loosely described. For example, they appear as the characters of the chiral algebra of various C=1 free boson theories at rational values of the radius squared. And so a lot of the work that I've been doing with Jeff over the past few years has been related to developing a story similar to Umbral Moonshine, but for functions that transform like this instead of like this. And I'll just flash the function corresponding to the first case, m=1 of this Penumbral Moonshine, because it's very striking in that the things that I've underlined in red are precisely dimensions of irreducible representations of the sporadic group on the nose. And they're huge numbers, and so the moonshine is essentially screaming at you in the face. So actually this m=1 case, Jeff and I worked out when I was an undergrad here at UChicago. And I remember working on this, and it was sort of like trying to solve a Sudoku puzzle from hell. And that it starts off very slow, and you sort of like don't really know how to proceed. And then by the end of it, you have a few more entries in the Sudoku table left, and everything's coming together, and you're just like throwing down numbers. And so I located in email form that point in the project for us. I remember I was sitting in the Regenstein library at 2 a.m. and I was just spamming the living hell out of Jeff's inbox. I think I sent like 8 more messages that night, but it's sort of a testament to the atmosphere that Jeff cultivates in his collaborations that I felt comfortable sending him tons of exclamation marks at 2 a.m. in the morning. And Jeff has always given me space to express my ideas comfortably and openly, and this has been like very indispensable for me as I come of age as a physicist. So I just want to say thanks a bunch for your mentorship. I'm going to skip this. And happy birthday, Jeff.
Time for one or two quick questions.
What did Jeff write back?
I was not awake at 2 o'clock.
No, I didn't see right away, but after seeing the stream and the.
You know, I didn't want to read too many emails because
Yeah.
going back 7 or 8 years and reading emails that far long ago is a health risk to anybody. I was worried about cringing myself to death, so I don't remember is the answer.
I guess if I was only good. So I don't know if this is the same thing or not or related, but my understanding is that on the Narain lattice, you get, instead of discrete gauge symmetries, you get continuous gauge symmetries at special points in the moduli space.
Yep.
My understanding is that those don't combine, those combine into some infinite dimensional group, as far as I understand. You can't think of them all as a subgroup of some finite dimensional group, even though there's a biggest one, they don't fit into a finite one. I think this is old work from the 90s or something. So it's should we be comparing these problems? And is it interesting that in the K3 case that these discrete gauge symmetries do combine into something?
So I'm trying to understand your Narain example a little more carefully. So I know, like, if we talk about C=1 free bosons, then, well, the chiral algebra of the theory enhances at every rational value of the radius squared. And maybe what you mean by enhanced symmetry is something stricter, which is that at R=1 in some units enhances from U1 to SU2? Or do you mean something?
Could I maybe?
Yeah, please,
try to
please, please
answer?
go ahead.
So there is an approach to trying to understand M24 moonshine, which has been partially but not completely successful, which is that you should look at different points in the moduli space where you can have different symmetries and find a way of multiplying group elements that appear at different points in moduli space.
Yeah.
Now, Greg, if he's here or listening, will complain that no one has actually defined that super carefully because you need some notion of parallel transport of the group elements. But nonetheless, in a limited sense, it's been carried out and you get groups that are a little bit bigger, but not as big as M24. Presumably, you could do the same thing in Narain moduli space. You could try to take
You just said the Conway one.
What?
You just said something about Conway one, which is much bigger.
You don't get all of Conway one, you get subgroups of it. Quite subgroups that are much smaller than Conway one. Anyway, the goal is to get M24. But I mean, you could try to do the same thing in Narain moduli space, and that might be an easier example of this symmetry surfing program, which is maybe there is some group that's much bigger than any group that you could get at any point in Narain moduli space, which you get by multiplying group elements at different points in moduli space after you've defined some notion of how to, parallel transport and then multiply group elements. I don't think that ideas have been explored in complete depth yet. But neither has it succeeded in giving M24, so.
I have a naive outsider question. I'm not in this. Are these two partition functions that you compare, K3 and the Narain problem, are they both counting BPS states or either or what?
Narain is not counting BPS states.
That's right. So, but here he's counting BPS states.
That's right.
So for BPS states, you have more right for them to be organized into groups which don't really exist. Because once you have them as BPS at one point, they will continue to be BPS elsewhere.
That's right.
It's not the case for Narain. For Narain, they go up and down, as you know. So there's no reason to expect.
Well, unfortunately, they also go up and down in K3 in that as you move in the moduli space, you get pairs of BPS states with opposite values of -1 to the F, which cancel out in the elliptic genus, but are nonetheless there. So when you get like a 45, there are points in moduli space where 45 plus 45 is not 90, but 96 minus 6.
Yeah, but the discussion is only about the.
If you know what I mean.
Yeah, but no, I know exactly what you mean, but the 45 plus 45 remains invariant everywhere. So there is something.
The difference is
remains
invariant. That's right, the difference.
That's not the, so this is the thing that should be organized.
Well,
Whereas the.
I agree there's the
not-
difference of the BPS property. I agree. But mathematically, there might, it's, well, Greg, yeah.
I was upstairs in the atrium, so I actually came down.
I knew if I invoked your name, you would come down from the heavens.
I specifically came down to complain. Yeah, I mean, with the search, I mean, it's actually a very serious and very interesting problem, that to make sense of symmetry surfing, you have to be able to define a flat connection on your bundle of conformal field theories over the Rayhaun moduli space or K3 moduli space. And if you don't do that, a flat connection, which is T-duality invariant. If you don't do that, then I insist that the concept is nonsense.
But it seems like there's a special class of K3 surfaces, which I think is basically Z2 orbifolds of T4, for which apparently you can do that, or at least.
Well, they chose special paths.
Yeah. Anyway.
Okay, let's thank Brandon again.